believe it's a few $100, and you get to attend all 4 days of sessions. So it's a great thing. So I'd like to introduce Dave Hutchieson. He's our presenter today. I don't know much except that we have something in common. I'm from Montreal. He visited Montreal during the famous ice storm of, I think it was 1996.
Yeah.
And if you haven't heard of that or haven't seen anything about that, go look it up. It's on the internet, and you can see all kinds of crazy pictures. There was a foot of ice deposited, solid ice deposited in Montreal, took down all of the power lines into the city, and basically you were marooned there for days, up to a month. And I had just moved out of Montreal right before that occurred, and he just arrived at the same time. So, but anyhow, that was a really
unbelievable. All the power lines got pulled down. The rain just turned to ice instantly.
Yeah.
The big to do.
very strange event.
Very strange.
Anyhow, I will turn it over to you.
Thanks.
Everybody's looking forward to hearing from you.
Thanks, right. Well, first of all, thanks to everyone at INCOSE, Dr. Hammond, Ian, Link, etc., for inviting me here today. It's going to be a somewhat unusual talk tonight, but you'll see as we go on why we've got the title here. A few admin things. You'll see me blinking a lot. I lost the sight in my left eye about 4 months ago. I was interrogated in Yemen 30 years ago, and this was the end result. So I've had 2 major operations. I've got 2 more to go. We managed to get the 50% of the sight back. So you're going to see me doing a lot of blinking while I'm doing that. Also, if you hear me coughing from various military accidents, I've got a problem with my trachea. Anyway, we'll put that to one side. So the title of tonight's lecture is Satellite System Engineering and Biomechanics, Applying Spacecraft Engineering Principles to the Human Body. And as we go along with this, you'll see why it's titled so. That's my contact details there. I've handed out a couple of cards to folks. If anyone doesn't have one, let me know. On the back of the card, you'll see a company that I'm working with just now, Bomax Hydrogen. We're going to be one of the biggest companies in the world in several years. We're producing pure hydrogen from just water, sunlight, nanoparticles, and soil enzymes. All major companies in the world have tried this, only got the reaction going for a few hours. They've now got it up to over 4 months. So you'll be hearing a lot more about them. Okay, so what we'll be doing tonight is just a little bit about myself. We'll cover satellite construction testing, launching satellites, types of orbits, orbital perturbations, we'll see what that means, biomechanics, excuse me, my personal injury in 2006, and my analysis and recovery using engineering principles. So as we go through with the talk here, hopefully some of this will make sense. Okay. So a little bit about myself. I was born in Scotland, a small village up in the Highlands. I took a degree in electrical and electronic engineering. I'm a member of the British IET, it's the same as the UK IEEE. When I was at school in Glasgow, I was a paratrooper in the reserve unit for 4 years. So I worked overseas for 25 years as a satellite communications engineer. I did 10 years work for the British government, working on large 100-foot, 400-ton antennas, which gave me a good understanding of systems engineering, feedback control systems, using motors with counter torque, etc., etc. We'll cover more of that later on. So we did a lot of governmental work, did 3 years comm support for NASA for the shuttle program. Britain had 3 islands important to NASA, Antigua, Bermuda, and Ascension. So what would happen is the shuttle would pass over, NASA would track it, they would get range data, velocity, communications, relay to us up to an Intelsat satellite, Andover, Maine, a DOMSAT down at Johnson Space Flight Center. So that was good, but it was extremely stressful. A lot of people don't know that during the shuttle program, excuse me, it wasn't just weather and technical reasons. every single communications facility and tracking facility had to be online and working. Otherwise, a launch scrub, and that was like $1 million a day in fuel, et cetera, et cetera. So it was good stuff. We did work for the American Navy and all sorts of different companies. So I did 10 years with the British government, and then I met my wife, Pam. She's from the States. We moved to Melbourne, Florida, and then I did 15 years all over the world. I traveled to a total of 135 different countries and territories. Not all working, sometimes I'd work in a place like Singapore or Malaysia or something like that. So all over the place. This picture here was very important for me. The parachute regiment is similar to the American Rangers. You don't just go in parachute school and put on a parachute. You have to do 6 months of intensive testing to get your Marine Berry. 2 hours after that picture was taken, another guy went through my parachute, and I had back pain my whole life. It changed my life forever in 2006. So this is not me, but this is basically what happened. So you jump from 800 feet, you get 140 pounds of equipment on you, you exit the aircraft, look up, check the canopy, make sure there's no one around you. You've got 80 guys in the air at one time, lower your equipment. But because of mistakes and wind, guys can go through your chute. You have less than 4 seconds in which to react. The only thing that saved us was that the ground was soft. But I had back pain my whole life, not completely debilitating, but in 2006, a disc herniated at the base of my spine, and that would change my life forever, as we'll talk later. Okay, a lot of people don't know what has come from Scotland. Most folk think it's whiskey and Sean Connery. There's a few more things. The United Nations has said for its size, Scotland has contributed more to the world than any other nation on the planet. First book in economics, Adam Smith, the founder of the Bank of England, the United States Navy, the telephone, logarithms, penicillin, anesthesia, insulin, etc. Isaac Newton had 2 pictures up on his wall of the people he admired most. One of them was Isaac Newton, and the other was James Clerk Maxwell. The fundamental theorems of electromagnetism, just about everything works on. So because of poverty, Scots were forced to learn things. We've got one of the highest percentages of university graduates in the world. But again, because of poverty, a lot of Scots went overseas. So this is, if you're a Harry Potter fan, that's the train there that's up near my house. We used to live pretty close to there. Surprisingly, if it's not pouring with rain and freezing cold, we've actually got beaches like that. There's an area in Scotland where the Gulf Stream comes in. It's a 3-mile strip of palm trees there. But you step out of that strip and you're wearing woolen jackets and pants. It's a very strange phenomenon. Okay, now, because this is INCOSE and you guys are systems engineers, we're going to look at satellites from a systems point of view. So we've got basically 2 main types of satellites that are used, what we call spinners, which are cylindrically shaped, and then tri-axis stabilized or box satellites. So some of the old satellites made by Hughes Communications, they were spin stabilized. They had solar panels on the exterior, and the dynamics of controlling a satellite are extremely complex. I'm going to be giving a technical talk to some students on the FIT on the 24th. We'll get into details on that. So what we're going to look at, what sort of subsystems does a satellite have? Well, it has an electrical subsystem to give us power. It has a thermal subsystem because a satellite is working out in space, and this is a very bad environment for anything. You want to try and keep the electronics at room temperature, but you've got the sun in one direction, you've got the colder space, you can pass through the Earth's shadow depending on the altitude of the satellite. You're trying to keep the electronics at room temperature roughly. So we'll talk about that later on. You need to have an attitude and orbit control subsystem. When the satellite comes out of the fairing and the rocket, it doesn't know where it is. So you have to have sensors that are going to look for something stable. You have Earth sensors, which use an infrared location system, sun sensors, the sun's a broadband electromagnetic radiator, and now on a lot of military satellites and some star sensors. You put a map of the stars in there. The satellite doesn't know what it is. It starts movement thruster, click, 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 until it locks onto a star. Okay, that's one reference axis. Now we need to get on to others that look for the sun and the earth. But we'll cover that later on. So where do satellites get their power from? Some scientific satellites use a radioisotope generator, for instance, the Cassini mission from NASA. So what will happen is radioactive material will decay, that will produce heat, and then you have a thermal to electrical conversion system with that. But although it's efficient, there's a lot of social problems. People don't like seeing rockets going up with a quote-unquote nuclear payload in it. But if you saw the testing that's done for these systems, it's absolutely incredible. And they can easily withstand an explosion. So we're going to look at rocket launch vehicles later on. This is a hot topic now. Years ago, when I first started, there was only a few, the AIAA French ones, so Deltas and Atlases. Now there's a whole pile of different ones. This is what we call new space. These are young engineers. I meet them all the time at conferences. Great young kids who've got all sorts of new ideas about space. Okay, so one of the standard things that we have on a satellite are solar panels. We've all seen pictures of these with solar panels sticking out. You have to keep them pointed to the sun. So there's actually mechanical components in there. You'll see that as a geostationary satellite moves around the Earth, we need to keep the antennas pointing to one point, but the actual solar panels need to rotate in synchronism. So there's electric motors in there, and there's bearings, and we'll talk about materials in a while, because you can't just use the same materials that you use in planes. So what you're going to do is you'll have subsystems in here with regulators and converters. Most of the equipment is going to use DC voltages. So you will take the raw power from the solar panels, you'll clean it up. This represents one of the sort of bearing systems as the solar panels are moving. And then you have buses. Standard voltage there is 28 volts. Some of the equipment, like traveling wave tube amplifiers that we use to amplify the communication signals, those need fairly high voltages. So we've got equipment that works in the opposite direction, taken from a low voltage up to a high voltage up there. So lots of different problems. You have to make sure that inside the satellite, with all this electrical cabling that's going around, that you don't get interference, you don't get spikes that get produced, because they could propagate and they could affect the communications equipment or the sensors. So all of this has to be carefully grounded and shielded, and that's an art and a science in its own there. So the electrical subsystem, absolutely vital. Now, as we'll talk about later on, satellites in geostationary orbit, they're 22,300 miles above the equator. Twice a year, because of the tilt of the Earth relative to the sun, they're going to go into deep eclipse. So they pass behind the Earth. There's no sunlight. Now you have to rely on your batteries. So it's absolutely essential those batteries get kept topped up by the solar panels. And when all of a sudden the sunlight disappears, now you have to rely on your batteries. And that brings in its own problems. You can't just suddenly put the batteries on, because you could get a spike there. So there's conditioning and filtering equipment and all sorts of things in that. Now, in the early days, a lot of the batteries would use liquid chemicals in there. And that brought about its own problems, because as your systems engineers, you know that if you change one thing, it can have a ripple effect in everything else. So with the thermal subsystem, you want to keep the batteries fairly warm, so when you go into eclipse, that the chemicals inside don't freeze, they don't crystallize and change what's going on there. So there's a bit, power balance is a very, very important thing in a satellite. And you want to have as many backup systems as possible. But that brings us back to the old business of systems engineering. Okay, it's great to have backups. Now you've added more weight. The rocket, as we'll see later on, has a particular diameter of the nose cone. You can only fit a certain size in there. So if you want to add more redundant equipment, where are you going to place it? It's a real complex business designing a satellite. And it's all systems engineering. It's you pay Peter and Rob Paul and et cetera, to come a semi-optimal solution there. Okay, satellite eclipse. So as I mentioned, the geostationary satellite, because the Earth tilted, I think about 23.5 degrees as it's going around the sun, and the satellite's going around the equator like this, the satellite can pass into eclipse. And this is extremely abrupt. So now we have to look at material science. You have one side the satellite's very hot, it's well over 100 degrees Celsius, more than boiling water. Suddenly, boom, you're going into eclipse. Way below freezing on there. So your materials have to be made so that they don't just crinkle. They had to learn all of this by experience of the old rocket missions with the Vanguard, etc., and Intelsat 1. Now, I'll talk a little bit about low Earth orbit satellites later on. We're going to focus here on geostationary satellites. LEO satellites are much in the news. Elon Musk's Starlink system, OneWeb. Jeff Bezos has got Kuiper almost ready to go up. Within the next few years, there's going to be over 40,000 of these small spacecraft up in orbit. Now, of course, I won't get into it, that's a whole separate talk, but there's issues with astronomy, with reflections. There's the horrible issue of the Kessler effect. You know, we've already had a Russian military satellite colliding with a French satellite. You get bits coming off, and then they can hit another satellite, etc., So this is becoming a big issue, and it's a whole separate industry now. I've been a number of conventions. There's one coming up in Orlando, 28th of January, called SpaceCom. That's really interesting. A lot of new companies there have got devices that will go up and grab this debris and take it back down. So the North American Air Defense System, NORAD, they're literally inside a hollowed out mountain. That's the Cheyenne Mountain Complex. So those guys are connected to radar systems all over the world that monitor what's going on in space, the debris. But it really is becoming a major problem now, not only for collisions, but also when NASA and other folks are launching up to the ISS, etc., you have to make sure that during the flight path up there, there's nothing coming around, whizzing around. A little fleck of paint hit the space shuttle window once at 17,000 miles an hour, and it went through 3 of the layers there. So, you know, even a tiny speck can cause major problems because of the momentum, the impact force that comes on there. So you'll see here we've got reference axes, and we're going to talk more about that later on. This is all to do with how the satellite orients itself and knows what it is. Okay. So, satellite eclipse, as I was saying, the Earth is tilted at an angle. This is what gives us the seasons. If we're in Florida, it's not too bad because we're fairly close to the equator. But if you're way up north or you're way down south, then you definitely see this. So you can see here, here's the sun. The equator is tilted and the satellite is going around the equator. Now, why the geostationary orbit? Well, there was Arthur C. Clarke who proposed this. He was the sci-fi writer that did 2001 Space Odyssey. So he was an RAF radar engineer. And way back in the 40s, he said if we can take 3 satellites 120 degrees apart and at 22,300 miles above the equator, we can cover most of the world with the exception of the polar regions, and that's what's been used for years. So the geostationary orbit, you'll hear a lot of people saying the satellite's going at the same speed as the Earth. Not quite, it's going at the same angular velocity. So if you look at the center of the Earth, and we need to talk about that later on, because there's 2 different centers of the Earth, looking at geodetics. So if you look at the center of the Earth and coming up like this, then the satellite at 22,300 miles has got this constant angular velocity. We'll look at orbital perturbations later on because the satellite and the Earth don't exist on their own. We've got the sun, we've got the moon, we've got planets, we've got the fact that the Earth is not a sphere, and and there's all sorts of things that go on with it. We'll look at that later on. So a couple of times a year, the satellite goes into the Earth's shadow, and that's when the batteries have to work. We have another strange thing called sun interference for communications, where twice a year in the spring and autumn, the satellite, the sun, and the communications antenna are all in line. And the sun's a broadband radiator of electromagnetic energy. There's all sorts of frequencies from very low to way beyond gigahertz, etc., etc. And that can actually shut off your communications. So we'll talk a little bit about that later on. Now, the thermal environment. This depends a lot on the orbit of the spacecraft. The thermal analysis for a low Earth orbit spacecraft is much different than that for a geostationary bird, or for one of the NASA missions, the Cassini mission, for example, the new site mission that's just been launched. So, a few things. First of all, we have solar radiation coming in. Now, the amount of solar radiation received depends on the surface area the satellite presents to the sun. So if it's a very thin satellite like that, and you were on there, you wouldn't have too much. But if it's pointing like that, which you normally want, then it depends on the surface area there. So we have inverse square laws and things like that for the amount of energy received. So solar radiation. We then have a thing called albedo radiation, and this is actually quite large. This is solar radiation that's reflected from the Earth back up to the spacecraft. And then we have planetary radiation. So the Earth is constantly sending out thermal energy because of the molten magma core that we have inside. So the satellite is picking up heat from all of these things, but also from the internal electronics. So as the amplifiers are running along, all the communications equipment is all generating heat, and we somehow need to balance that. When the satellite was in a very cold area, we need to activate heaters, but when the satellite is in normal orbit, and one side's facing the sun, the other's in cold space, there's a massive thermal gradient, and we still have to compensate for that, for the electronics. We'll see how to do that later on. Okay. So heat pipes, these were one of the first things that were used in satellites for getting heat from one area to another. Now we've got a problem on Earth. When you look at thermodynamics, we've got radiation, we've got convection, which you see with boiling water, we've got conduction, all sorts of things there. Up in space, one of the main things that you use is radiation, because you really don't have an atmosphere up there. Now, even at 22,300 miles, there's a tiny amount of atmosphere. There's a few particles up there. At low Earth orbit, when we're doing orbital mechanics, this is how we figure out how a satellite is going to get from A to B, what angles it's going to go through. They're called Keplerian elements, and we'll look at that later on. In a low Earth orbit satellite, the heat signature is much different than it is up at geo-orbit. So one of the things that we want to do is we want to try and get heat from one place and then dump it out by radiation to another. So if you've got a whole bunch of electronics and they're all getting pretty hot, you want to take some of that heat and you want to get it to a place that's facing cold space and radiate out. But this brings us into a big problem. Fluid mechanics in space. I'm going to be talking to some of the students at FIT about this in a couple of weeks. Fluids do not behave the same in space as they do on the ground. Now, you see the astronauts on the International Space Station, and we say they're in zero-G conditions. Actually, they're not. The force of gravity is about 90-odd%. So how on earth are they floating? What's happening is, roughly, is the ISS is sort of falling at the same rate that the Earth is falling away there. So they are not in zero-G conditions. You have to go way, 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 way up before you get back. So NASA's got a really nice technical paper on that there. But we always say zero-G. Okay, so what they found out was with certain fluids on Earth, when you put them through a pipe, there's almost an electrostatic type of system that occurs where the fluid touches onto the pipe as it's moving through. What they found out in space in zero-G conditions is that the fluid doesn't go nice and smoothly, it goes in globules. So like if you're in your home and you get an air bubble in there and you turn the taps on and you get that shaking and noise, that's what used to happen. So what they did was they turned to technology that's over 2,000 years old. If you ever see an old oil lamp, so you've got the oil lamp there, you've got a wick and you've got the flame, but the fuel is down here, the oil. How does that fuel get up there? Through capillary action. So what they do is they take very, very pure cotton, it has to be made in special conditions with no impurities. And what will happen is this vapor flow will go from here to here, the heat will come out, and then this will condense, and some of the fluid will move back by capillary action. Because pumping fluids in space is a really, really difficult thing to do in zero-G. Okay, the next system that we need to look at is the attitude and orbit control system. So satellite comes out of the nose cone of the rocket, it doesn't know where it is. So one of the things that we can do is we can use these sun sensors here. So what happens is there's a little window. What it does is it's tuned, so to speak, electrically to certain frequencies. Satellite comes out, doesn't know what it is. Thrusters are fired to move it around. We've had a big pulse of energy. That's the sun, the lock there. But now we don't know if we're upside down or not. So now we have to have another window. The Earth. So the Earth sends out infrared energy. So what you can do with satellite is you can have a window tuned to that. No signal, bang. You hit the edge of the disk. So now, if you're on the equator, you should see a measurable amount of energy going from one part of the disk to the other. But if you're above that or below that, it will be a smaller amount. And then you can fire thrusters to bring that back on. So there's this dynamic system that's going on. There's very complex control algorithms that go on. GPS, yeah, you can sometimes use GPS, but that's actually quite rare. Most of the time we use what's called reaction wheels and momentum wheels. Now, an important thing are these thrusters here. So the thrusters fire a little bit of gas. Sometimes it's nitrogen tetroxide, sometimes it's dimethyl hydrazine. It gives a quick pulse. Now, when we look at propulsion systems, a very important thing is what we call specific impulse. I'm not going to get into all that here, but how much oomph you get per pound of fuel, we'll call it that. Some fuels are more efficient than others, but there's a drawback. Hydrazine is a very, very toxic fuel. If you breathe that, it can actually kill you. And also the fact it's highly corrosive as well. So there's all sorts of new fuels getting used for thrusters. Right, now, when the satellite is in orbit, conservation of angular momentum, this is a huge thing. When we're doing orbital mechanics, we're designing how satellites go around the Earth, and when you do the orbital mechanics of a satellite fly by, there's all sorts of horrifically complex equations. It's much better leaving that to a computer. For the simple stuff, the Keplerian elements and things, that's no problem. You can do it in paper. But when you're doing things like flybys, that's massively complex. But there's two principles that always apply: conservation of energy and conservation of angular momentum. Now, what we do in the satellite is we have wheels which spin. They're called reaction wheels. And what can happen is if there's a disturbing torque. Now, what could be a disturbing torque? Well, in space, there's tiny little particles that are constantly bombarding the satellite, little micrometeorites. There's solar pressure. If you have the satellites turned so that more area of one solar panel is facing the sun than the other, it will actually generate a very tiny torque on that satellite. It generates a force. Aerodynamic pressure. This is important for low Earth orbit satellites, 200, 300, 400 miles up. There's not much air, but there are particles of it. A and that causes degradation. That's the main reason why the Starlink satellites eventually decay, and they have to bring them back in and burn them up. Okay, we'll talk about geostationary satellites later because they're extremely expensive, and you want to do something to stop that satellite from decaying. So we'll cover that later on. So the total angular momentum is made up of the spacecraft moment of inertia here times the angular velocity plus the moment of inertia of the wheel times the angular velocity of the wheel. So that what can happen is that when we have something that causes the satellite to move a bit, they're called perturbations, and we'll cover this more later on, you want to keep this equation constant. So what we can do is we can speed up the wheels or we can slow them down to keep the angular momentum constant, and that tends to stabilize the satellite. But there's a problem. We get what's called wheel saturation. So these are literally wheels spinning at fair old speed, and they're in very special sealed containers, almost like the old hard disks that you had. So what happens when you reach the maximum mechanical speed of that wheel and it can't go anymore? Now you have to do what's called a momentum dump. You have to fire thrusters very carefully to get rid of some of that momentum there. You've got to be really careful because you don't have friction. So on the ground, you're driving your car, you put the brakes on, okay, you slow down gradually. In space, you fire those thrusters and you switch them off. That spacecraft just going to keep moving. So sometimes you have to use a counter thruster to do this. And this is a real complex business. This is why the flight controllers, the guys on the ground, they're extremely skilled with this. I'm not going to go into details, but there's a certain nation launched hunter-killer satellites which followed our reconnaissance birds very, very closely. And they did that so the controllers could get experience in firing the thrusters, switching them off, and coming close up to our satellites. So that was all over the news a few years ago. It's a very complex process. So reaction control wheels, we usually try and mount them mutually at 90 degrees, an X, Y, Z type axis. And then you have a backup as well, because if one of these fails, that's not a good thing. But they're complex, and the software that they use is quite detailed and expensive. So for propulsion systems, we can use cold gas thrusters. We can take a gas, which is compressed in a tank, and then we can open a latch or a valve, and all of a sudden, some of the gas comes out. So just think of it like a fire extinguisher. We've all seen, in movies and things like that, someone sits in an office chair to watch the office comedy show. They fire the fire extinguisher, comes out, and they shoot back action and reaction there. But they have to be very, very careful with what comes out, because a satellite's divided into two systems, bus and payload. So the bus is thermal system, electrical, all the stuff that supports the payload. So the payload's either communications, Earth observation, it could be GPS, etc., etc. If you have sensors there looking down in the Earth, and you've got a dirty fuel, when you fire that, some of that can come out and can end up in the window of the sensor. So this is a whole complex business. Now you have to look at particle patterns coming out of the thrusters. This should all be done in the ground to make sure that those particles don't end up on the sensors there. Okay, so a standard type of fuel is monomethyl hydrazine and nitrogen tetroxide with an oxidizer. So what we will do is, a lot of these fuels are kept under pressure, because if you don't keep them under pressure, you'll end up what's called fuel slosh. And that's a real complex business. I'll discuss more about that later on. Okay, ion thrusters are becoming really big. NASA has a number of spacecraft now that are using them. It's slow, takes a long time, but it's very useful for interplanetary missions. So basically what you're doing is you're heating a substance up, you're producing electrons here, ions are produced, you have an electromagnetic field, you accelerate the ions out here, And they're using that now in commercial satellites. It's not as fast and responsive in many cases as with the old thrusters, but it does a lot of applications there. So that's one of the things that they're looking to use for future missions from Mars and beyond. Okay. TTCNM, tracking, telemetry, command, and monitoring. So when the satellite's up there, it's doing something. It's measuring stuff in the Earth. It's listening into phone calls of people we shouldn't be communicating. It's checking down in the Earth to see what crops are good, what crops don't have any, etc., etc. So we want to know the health of the satellite. Are the battery voltages good? Are any of the amplifiers having problems? What are the pressures of the fuel and the gases? So what we do is, if that information is in digital form, fine. Otherwise, we use an analog to digital converter, create some little bits, and then we use a device called a multiplexer. So the multiplexer takes all of those bits together, coming in parallel, and we feed them out in serial. So now what we need to do is, we need to take what's called a beacon signal, and we'll take a break in a minute for this. A beacon signal is like a flashlight from space. It's at a particular frequency. So the Intelsat satellites use them at 3947.5 megahertz, 3952.5 megahertz, and others. They're up in the gigahertz band. So it's a clean signal we take as a carrier, and then we modulate that data on it using what's called phase shift keying. So what you can do is for a 1, you keep the carrier at a particular reference. For a 0, flip it over 180 degrees or something similar to that. So you're going to take the information about how the satellite's doing, modulate it in the telemetry beacon, send it down to Earth. Now, when it gets down to Earth, you go through the reverse process. You demultiplex all the data. And then at these satellite control centers, you've got all these guys sitting there at computer screens, just like in mission control. One's going to look at the thermal system, one at the electrical, one at the communications, and they all look at that telemetry data. Okay, next thing, tracking. We'll see in a while that a geostationary satellite doesn't just stay in one position, it actually moves in a figure-of-8 pattern due to these perturbations that we'll talk about. So you have to track the satellite. Now, you use fairly big antennas for that at what are called C-band frequencies. They're around about 6 gigahertz, 4 gigahertz. A lot of modern satellites are using much higher frequencies, Ku band, Ka band, all the way up 30 gigahertz and higher. But as with systems engineering, you pay someone, you take away from someone else. So as the frequencies get bigger, the gain of the antenna gets bigger, and the size of the antenna can become smaller, so balanced, but the beam width becomes much narrower. And the waveguide plumbing, we use waveguides to send electromagnetic information from the amplifier to the antenna. Some of that is just absolutely tiny. So, but they managed to get to overcome all of these problems. So tracking, you want to know if the satellite is behaving properly. So you have to have a very accurate, calibrated antenna that follows that satellite, and that's a real complex business. So I worked in these big 100-foot, 400-ton antennas, right? Huge antenna, but very narrow beam width. Now, you want to move the antenna to point to the satellite, okay? You start up the motors, they have to overcome that 400 tons of inertia. Now you want to stop it. Well, you can't just stop it because it's going to overshoot. So you use what's called counter torque. It's an electric motor working in opposite direction. So imagine someone pushing a wagon fast and they want to stop. You have someone at the other end doing like a retro push there. This gets a real complex business. When you're getting those big antennas to move, NASA's got the Deep Space Network at Goldstone, Arizona, Madrid, Spain, and then down in Canberra. Those things are huge, and mechanical engineering is very interesting. Okay, TTC, C, command. You want to send a command signal up the satellite. If there's an amplifier failing and the equipment hasn't detected that and switched over, you might try sending a command signal up to do that. Now, that raises an interesting point. When the first satellites came out, especially the TV satellites, that wasn't encrypted. And if anyone remembers way, way back, I forget his name, he was a guy, I think he called himself Captain Knight or something. He overrode a satellite transponder with a signal. I think it was HBO that were transmitting. And he was making a statement, you know, we don't want to pay for cable TV. He actually sent a signal all the way up there and it overrode what was coming in one of the amplifiers. And there's also people have sent up command signals to satellites. Nowadays, that's very difficult to do. Everything's encrypted. But up until not all that long ago, you could take a fairly small dish, and if you knew the frequencies and you knew the command signals, you could actually send commands up to spacecraft and they could do things. Monitoring, communications. So when a satellite's sending your TV signals down and your phone data that's coming down, you want to monitor that to make sure the power levels are correct. We have a thing called EIRP, effective isotropic radiated power. This is a measurement of power taking into account the gain of the antenna. And we want to make sure that the customer paid to get a certain amount of power. So a satellite can send out a beam. We have what are called global beams. They'll cover about a third of the Earth's surface. A hemi beam, North America, South America, Asia. Zonal beams, very highly focused. So imagine those mag lights, you know, those flashlights that you adjust. If you open it all the way up, like that, that will cover part of the room and you could look at it. That's like a global beam. But if you focus that right down to cover just a spot and you try to look at that, it could blind you because the amount of energy per square meter is very, very high. So it's the same with a satellite system. We'll take a break in a minute too. Satellite transponders for communications. We have a signal from the ground. We're going to boost it up. We're going to mix it with another lower signal and send it down another frequency band. Why do we have two frequency bands? Okay. The signal coming up from the Earth is extremely weak. It's a tiny, tiny amount of power. Now, the output signal is very, very large. The two antennas are very close together. If some of that high power leaked into the low power area, we have a thing called the Barkhausen criteria for oscillation. You can end up with oscillations there. So that's one of the main reasons why we split the frequency bands there. Okay, I think we'll take a little break for just now. Okay, so now we're going to do a very unusual thing. We're going to apply satellite systems engineering to biomechanics of the human body. You can see there are a lot of connections. So, and this might help some of you who have back pain, etc., etc. I've given out my card. I've helped over 400 veterans get their lives back with back pain. They've been told nothing more can be done if I'm using an engineering analysis, which I had to do for myself. So, in a normal spine, there should be 4 curves. One up in the neck, cervical, one in the upper back, thoracic, one in the lower back, lumbar, and one down here, sacral. We'll forget about the sacral one just now. All of these curves are intertwined. You make a change in any part of the mechanical system, and one of these curves, it will affect the others. Why are the curves important? And doctors don't seem to realize this, so we'll talk about this in a minute, but as engineers, you'll get this. Okay, so there are building blocks in the spine, and they're called vertebrae. They're made of bone, they're very, very hard. So we have all of these building blocks that run up and down the spine, and they interconnect with each other. Excuse me. So there's a little hinge here, and a little hinge here, and there's a hole we call a foramen, but that hole can increase or reduce in size according to the curvature of the spine and also the thickness of the discs. Now, these discs act as shock absorbers. So when we have a perfect spine with all the nice curves and we have a vertical compressive force, these discs are designed to squirt that force out laterally. Now, the disc itself is made up of 2 components. There's a jelly-like center we call the nucleus pulposus. It just means jelly-like center. And then surrounding it, a series of rings is called the annulus fibrosus. So a healthy disc is 80% water. Think of it as a shock absorber, right? It's a shock absorber in the car. Now, herniated disc. I had one in my lower back, and it was really, really bad. The center of the disc had gone right into the spinal cord. The pain was absolutely horrific. What can happen is that if there is too much pressure, the disc will dry out. If you take an onion and you split it in 2, fresh onion, you apply pressure, you will get a little bit of give on there. Now you leave it out in the kitchen counter for 2 weeks, it becomes really brittle. You press in it, the whole thing will break apart. So what happens is when the water comes out of the disc because of excess pressure, and we'll discuss that excess pressure in a minute, the disc becomes brittle. Its mechanical factors change. And the center of the disc, this nice gluey ball of material, the nucleus pulposus, which is responsible for transferring all these loads, it becomes dried out. When the rings dry out, you can't see them on here, but there's all these rings, becomes brittle, that disc can burst through. But just because an MRI shows a herniated disc doesn't necessarily mean that the pain is coming from there, as we'll talk about in a minute. So, from an engineering point of view, here we have a biomechanical system. We've got a spine, which is like a spring. So if we apply a vertical force with these curves, we expect that spring to just sort of absorb. The curves mustn't be too deep and they mustn't be too shallow. Terminate a robot. How does it move its neck? It has pistons here. So if it wants to move the head over there, the piston contracts and this guy expands. If it wants to go the other way, this guy contracts and that one expands. Now, if we have good materials and good lubrication, we would expect a piston to be able to run for years. What about muscles? If I take my arm and I do the same thing, biceps contract, triceps expand, biceps expand, triceps contract. Could I do that all week? I don't think so. You'd be in agony. But why would you be in agony? What is the difference between the muscles in your arm and that piston? We'll cover that in a second. So here we have the muscle action here. One muscle shortens, the other guy expands, and vice versa, depending on the movement. So now we have to take a look at how muscles work. So with a car, we take in air and fuel. We burn the fuel and air in the engine, it creates energy, and the pistons start to move, and the pistons then transfer that energy into the drive shaft, and from the drive shaft into the wheels. Great. But what about waste products? When that fuel is burned, it creates exhaust, and the exhaust contains all sorts of nasty stuff, carbon monoxide, etc. But no problem, we just stick it out the exhaust pipe and it's gone, and we carry on our journey. When a muscle is going to be used, it takes in blood, and the fuel are the sugars that we get from eating our food. So the sugars are the fuel, and it also takes in oxygen, and it quote unquote burns the sugars with the oxygen. It's a biochemical reaction. That produces energy, which then allows the muscle to move. But there's a problem. When that reaction takes place, just like the car with the exhaust, we create waste products. There's three main ones: lactic acid, hyaluronic acid, and carbonic acid. And we run into a problem. Those waste products react with organic compounds to form a glue, a literal glue. It's called an adhesion. And that can restrict the muscle from moving. It can make the muscle shorten. But if the muscle shortens, what's it attached to? It's attached to bones. And the bones are basically non-compressible. So if the muscle shortens and we can't get it length, we've now moved bones of the body out of position, especially the spine. We have changed the curvature, which in turn changes the pressure on the discs and changes the pressure on the muscles. This is why these curves are so important. So acid buildup, lactic acid, that's what you get when you were in gym class at school and you had to climb up ropes and you were running around. You got that stinging in your calves and in the front of your shin there. That's the lactic acid buildup. Now, in a healthy muscle, what will happen is the lactic acid will come out of the muscle, go into the bloodstream, into the urine, out, and everything's good. But if the muscles are not stretched on a regular manner, you'll see people in China doing Tai Chi. That's for multiple reasons. It's helped the sense of balance, but it's also gently stretching those muscles. These adhesions build up, and they can build up to a state where that muscle cannot be released. So it shortens muscle. Now, for anyone with back pain, even though it took me years of learning about neurology and electrical impulses and reflections and spinal surgery and mechanics, a lot of it boils down to this. When a muscle shortens from overuse, it pulls both ends towards the middle. If bones are attached to the ends, they will pull away from their normal positions. Posture can change, causing pressure on discs, muscles, and nerves. So we'll talk about that in a minute. Psoas muscle, the number one muscle for back pain. Every single person I've seen, including myself, this was a major problem. So Western lifestyle. This muscle attaches to the bottom of the spine here and to a little bone on here called the lesser trochanter. So from an engineering point of view, we've got a fixed fulcrum. That bone's not going to go anywhere. When we sit all day long, which we shouldn't be doing, in Asia people squat, but modern life and these computers, we're slaves to these, we have to sit. We sit for TV, we sit for breakfast, we sit at the car, we sit all day with these. So what happens? The muscle contracts. If it is not stretched properly, adhesions build up and the muscle stays short. We now look at the spine from the side. This guy is in the front. It increases the lumbar curve. That causes pressure on the discs and the muscles. Nearly all back pain has nothing to do with the back. The back is reacting to changes in the dynamic system on the front. Now, we might say to ourselves, if I'm standing here, is this a static situation or dynamic? Static, I'm standing here. No, it's actually dynamic. Every muscle in my body is moving right now. Tiny microscopic movements trying to keep me in balance front and back. So if you were to get a special microscope and go right in these muscles, you would see all of this twitching going on. So what appears static on a macro level, down in a micro level, there's a lot of stuff going on trying to keep the balance there. Now, this muscle here, if it gets tight on both sides symmetrically, what it will do is it will pull that spine forward and increase the curve. Number one problem people with back pain. I've never seen a person with back pain who doesn't have this as a component. It can either be a major component or something else. But there's a bigger problem, asymmetry. So when we have a mechanical system, it could be a launch tower, it could be an aircraft, etc., etc. If one side is shorter than the other, we can see that that system's not going to function properly if we don't have symmetry. So when babies are born, they're ambidextrous. They can use right hand or left hand. What they normally do is they look at what's called the dominant pair. They look at the parent that they react to most. It could be the mother, it could be the father. And often they will mimic that pair. So the mother is the dominant parent, right-handed will do that, or left-handed. And it doesn't work in all cases, but they've found out it works in a lot of cases. When the baby is in the womb, it is not lying there symmetrically. Often it is twisted like that. In Africa, there's a very low incidence of back pain. What happens is when the baby's born, they hold it by its feet and they take a cloth. The bones are soft, the muscles are soft, and they pull gently down from there. That means if the baby's been lying in the womb and one psoas is tighter than the other, it will stretch out. Now, to release that psoas as adults, it's more difficult. I can talk after the lecture about this. There's some things that you can use to do that. But if one side contracts more than the other, the whole mechanical system is going to tilt. So we have to look at that. Now, another muscle called the quadraxial morum, this guy attaches from the top of your hip to the bottom of the rib cage. Hip replacements, I'm going to say this, and I will argue with any doctor that wants to be in an engineering point of view, 80% of hip replacements are not required. What has happened is that the pelvis has tilted and it's put more pressure on one hip joint than the other. As simple as that. And I'll argue with any doctor about it. Now, there are cases where people have disease and they've had injuries. You would be amazed. I had a veteran and he was due to get a hip replacement. I said, send me your x-ray. Well, the doctors looked at it, send it to me. His pelvis was so tilted like that. I said, which side do you think has more pressure on it? Well, that one, yeah. So why don't we try and get your pelvis level and see if that takes the pressure off? So I worked on for a couple of months. We managed to identify the muscles that controlled that, released it, didn't need the hip surgery. It's very rare that you need both hips done at the same time. Usually what happens is one hip is done and then the body has to counteract that because everything gets tight from the scar tissue and then the other one wears out and the next thing you know you've had two. It doesn't always work like that, but a lot of the times it does. Now, what this guy does is, if you've heard of scoliosis, I had this very, very bad. The doctors wanted to put steel rods down my spine, but I got my wife to take a marker pen. She went down from my head to my tailbone. She pressed over 100 muscles. Every time I went, ouch, that meant lactic acid. She would mark it with a dot. We then took a photograph. I'll see if I've still got that. And you could see the scoliosis. She then used over 2 months her thumb to dig into those muscles, release them, lengthen them back. There's little muscles called the multifidi, they connect the vertebrae, and now my spine is perfectly straight, zero surgery required. So this guy here, if one side is tighter than the other, asymmetry, it will pull the rib cage down and pull that hip up. That will not only cause more pressure on one side of the spine, we're engineers, we're looking at something symmetric and then asymmetric, it's also going to pull your head over. So why doesn't your head stay over for someone with a tilted pelvis? The body has 2 mechanisms for balance. So inside your ears, deep in there, there are 3 semicircular canals. These are little bony, sort of half-circle canals at 90 degrees with each other, filled with fluid and little hairs attached to nerves. So if I push my head forward, the fluid goes back, the hairs go back, and it triggers the brain to say the head's going forward. But there's another thing. The brain does not like the eyes not to be level. The brain always wants to look for something level. The horizon, this roof in here. One of the reasons why astronauts get sick for the first few days in space. So QL gets tight here, pelvis goes over, and this happens in microseconds. Head goes over, brain doesn't like that, so how's it going to get the head back? It tightens these muscles, the scalene's in there, woof, the head goes back there. So, one vet that had migraines. Migraines are complex. Some of it's genetic, some of it's due to food, eggplant, tomatoes, but about 75% of migraines, it's muscular. And what had happened was his pelvis was out of place, which means that the brain had tightened up these guys, which pulled down in the scalp. So we worked on getting his pelvis level, getting these muscles, and then the brain relaxed those muscles there, and the migraines almost disappear. So this guy here, very important. If you ever get told that you need a hip replacement, get those two muscles tested there.
Call Dave.
Yeah. So here we are, pelvic tilt. This is exactly what I had. This is going to be caused by tight QL muscle pulling this hip up, or tight psoas muscle, or another guy that lies inside here called the iliacus. Very, very important. You've got back pain, laying your back, there's two little bony points, they're called the ESIS, anterior superior iliac spine. They're the highest points there. Laying your back, get someone to take a thumb and dig in there. If you go ouch, and more on one side than the other, there's a chance you can need a hip replacement. There's some back problems. So you should be able to dig in at least 2 inches with no pain. There's tools that you can use to do this and techniques. I'll talk about that later on. So, your biomechanical system, just like the satellite antenna, these big satellite antennas, if the mounting structure was not level, you're going to get all sorts of asymmetrical forces, which is going to cause pressure in the system. So you should have shoulders level, pelvis level, knees level. Now, at one point, I had one shoulder down like that. So the doctor goes, don't worry about that. Everyone's like that. No. Where did that come from? Well, it could come from a number of things. It could come from a tight pectoral muscle, which causes the shoulder to rotate forward and up, or it could occur from the QL muscle pulling the rib cage down and pulling this down. The old thing, the knee bone's connected to the knee bone, etc. Very, very true. It's a whole mechanical system. So we have to look, first of all, at what's not symmetrical. This is what I do with veterans. They send me 4 pictures, front, back, left and right wearing swimming trunks. So I can look at things, even look at the belly button. If the belly button is not in the center and pulled over and they haven't had an unusual birth, it means that some of these muscles in here have tightened. There's all sorts of things you can look at. You can even look at stress patterns in the face because the scalp moves. And you can look and see what's tight on one side, and that gives you an idea of what's going on there. So you must have shoulders, pelvis, and knees level. Now look what happens here. When that pelvis tilts, that knee rotates inwards. Tiger Woods, I saw this years ago with him. In fact, one of the guys that got me back up on my feet, he told Tiger Woods, I think he's had 6 surgeries now. He said, you don't need surgery. He said, you got tilted pelvis. And Tiger Woods said, well, Dr. So-and-so, who's the orthopedic, blah, blah, blah. So he said some real serious surgeries, and one of them was that. Golfing is one of the worst things for your back because it's asymmetrical. Okay, so get the old golf club. You're always doing either this or that. But golfers should really do this, although it's difficult. This all contracts here. Hit that ball there, but then try it from the other side. Because otherwise one side, that's why golfers got some of the worst back pain ever. And then their knees give up because of the way they're standing. If something is on one side of the body constantly, you have to try and correct it by stretching it over to the other side. This is all engineering. Right, forward head posture, the big killer. My chiropractor has shown me pictures of 13-year-old girls with the necks of 18-year-olds. Why? This. So, how does the head move? There's a muscle called the sternocleidomastoid muscle. Bit uncomfortable, right? Sternal part attaches to the breastbone and sternum, cleido to the clavicle, and the mastoid process behind here. Think of it as a piston, right? So all day long, this, and the worst thing, if you've got a laptop, put a screen up here so you sit like I will guarantee you that for people within 15 years, they'll have real serious problems if you're doing this all day long. So this guy contracts, and if it isn't stretched, the adhesions build up and it stays short. This causes multiple problems. Number one, it pulls the head forward. You've now taken away 10, 15 pounds average head, and you've shifted at a distance. Force times distance, you created a turning moment. Why don't you topple over? Because the back tightens up to hold you up. In fact, in Latin, the name of the big muscles is the erector spinae. It means to keep the spine erect. So the back is constantly tightening up because that head is forward. Now, second thing that happens is the neck curve, the cervical curve, changes with more pressure. And these muscles tighten, and you get migraines, you get headaches, etc., etc. So you can see the quote-unquote pressure changes here with these movements, 12 pound, 32 pound, 40. But there's corrective exercises that you can do to stretch these muscles of that shortened piston to bring the head back. So that is a major cause of back pain. The head's forward, changes center of gravity, back tightens up. Okay, cervical degradation. You can see here that you've got a nice normal curve, but then after time on phones and sitting at laptops, this straightens out. You can get 10 times the pressure on the discs there. It's a very, very serious issue these days. Forward head posture. So the head moves forward, shifting the COG center of gravity. That's the number one thing to remember. To compensate, the upper body drifts backwards because you're trying to keep the system stable. To compensate for the upper body shift, now the hips tilt forward. When the hips tilt forward, you're putting pressure on the knees and the back. It's this whole dynamic chain reaction that occurs here. Now, a normal X-ray. I'm not going to mention the medical school, one of the most famous medical schools in the world. It's in everyone's lips in America, and you always see in the movies, oh, I'm going to X to be a doctor, and did you go to X? Yes, that's the best. They have this teaching of students as a normal X-ray. Can you see that tilt down there? That is not a normal X-ray. And that's what these doctors are being taught. So what has happened is that spine now has started to move out of position there. Massive pressure now is on that joint there. Over many years, that will start to wear out, requiring a hip replacement. On the front here is what we call the pubic symphysis. There's a piece of cartilage in there. For women, that can be extremely excruciating painful. So a lot of the solutions are simply to inject cortisone in there. Well, cortisone reduces inflammation, but only usually for 6 months, and it actually destroys the bones. This is simple engineering. That is not a normal X-ray, but that's what your doctors have been taught, in America and elsewhere. Now, I used to stand like this. I've never even noticed it. I didn't know my pelvis. One of my friends from Nigeria sent me this. I think it was down in South Africa. Look at that scoliosis there. Can you see that? I only found this out the other day because he took the photo before I could stick that knee out, which I didn't realize I was doing for all of these years. So again, the doctor said, oh, we have to put Harrington rods down your spine. I said, no, I'm going to do an engineering analysis, get my wife to dig her thumb in. Ouch, ouch, that's okay, ouch, put the dots on there, okay, now we've got a map, I'll see if I've got a photo at home. Now we knew where all the tight muscles were, then she had to use a thumb and release them, and then the old spine with the screw. So that was me in the Middle East. That was taken at the same time a particular country was about to invade this country here that could have started World War III. I won't talk about that just now, but that was a very scary period of time. Now, you see the way I'm standing there with that knee sticking out and the belt at an angle. This fellow, my friend here, he's just standing normally. So that was the way I stood. I had bad scoliosis, but I didn't know it because of the tilt pelvis. Short leg syndrome. I'll just do a few more of these here. You go to the chiropractor or doctor, you've got one leg shorter than the other. Really? The number of people who are born with one femur shorter than the other is like 0.0001%. So this was British Special Forces guy here. Horrible pain for 10 years. He'd spent $20,000 trying to get it fixed. So I said, okay, lay down and let me take a look at the legs. You can see how this leg appears shorter than the other. So I said, go to the doctor. Doctor said, yeah, mine's like that as well. Don't worry about it. No. What had happened was this iliacus muscle that lines the hip and attaches to the fulcrum, same one as was, had shortened. When it shortened, it rotated the hip forward and brought the leg up. It was an artificial short leg. So over 2 nights, I got him laying his back, the ASIS point, this bony thing here. I got his wife to use her thumb. She put gloves on because the nails, and she worked in that muscle for 2 days. And then the muscle released, the hip went back, the leg went down, the pelvis went level, the spine went straight, and 10 years of back pain disappeared using analysis. SI joint injury. This is where the chiropractor changed my life. So I said I had back pain my whole life. 2006, a disc herniated down here, L4, L5, horrible pain. What happens is that the centre comes out and presses against these nerves. So they put me in a decompression machine for 3 months and it worked great. It was about 90% pain-free. How does decompression work? Don't listen to anyone that says discs can never be reconstituted. In certain cases, they can. If you stretch the spine using a logarithmic curve, not a linear curve, not the old traction with the big weights over the end of the bed, what happens is these little muscles that join these bones are called the multifidi. They'll release, and you create a partial vacuum in the disc, negative pressure, and that sucks the herniation back out. So 3 months in that, I'm feeling really good. On the last day, he put me face down on the table, and this is the sacroiliac joint. This is your sacrum, and the ilium's the hip, least known joint in the human body. He lay me down, it's the tightest joint normally, and my wife said when he pushed down, he slipped. He ripped this joint apart, and it locked in the wrong position. Within minutes, I ended up in a fetal position. It caused a chain reaction through my body. The pain was horrific. Long story short, the doctor covered it up, chiropractor covered it up, the lawyers let the statute of limitations run out. I lost my life savings. We nearly ended up homeless, food stamps for 6 months. Anyway, we won't get into all that. But he covered it up. I then gave myself 24 hours to mourn. And then I said, I'm going to do something about this. I had no medical knowledge. So I started teaching myself to speed read, looking at keywords, putting them into my head, doing 5 pages at a time, coming back to that, studying it later on, buying all these medical books, neurology, how electrical impulses, and thought, oh my God, I just, this is too much. Let's go back to engineering. So I start buying models of the pelvis, the skeleton, etc. And I thought, this is a 3-dimensional object. They've only taken an X-ray from the front. Why aren't they doing it at 15-degree angles? Oh, no, you don't have to do that. I'm a doctor, I can see it. I says, but this is a 3D object. You cannot determine that complex curve. They wouldn't even listen to me. Then, this whole satellite business. I knew that in the early INCOSE-SAT-4 satellites, when they fired the thrusters for station keeping, remember we spoke about that figure-of-8 pattern. We want to try and get the satellite back in the center because the gravitational force, the sun, moon, etc., etc. When they fired those thrusters, the fuel would slosh. It's like water in a bucket. When it's sloshed, it causes a very complex mechanical movement called nutation. Remember that wobbling thing we spoke about earlier on? So I thought, what if that joint has mutated? It's moved in 3 dimensions. Don't ask me why that came into my head, but it did. So I go back to doctors in the wheelchair. My wife was taking me in, and I said, Dr. So-and-so, really well-known guy. He's the sports doctor. He's, operated with so-and-so. Not think he doesn't know about back pain, really. So I went in and I said, I think this joint's mutated. And he looked at me. I said, okay, let me explain. I think it's moving too. Oh, no, that joint doesn't move. Under normal circumstances, it doesn't move much. It moves in a microscopic amount. It's responsible for taking vertical forces when we walk and passing them out laterally in 3 dimensions there. What had happened was, when the guy laid me down on the table, all the ligaments relaxed, and that normally tight joint became loose. And when you pushed down, he slipped and he ripped this out of position, locked it in the wrong place, and when they got me up, all the ligaments tightened up again. They did not even know basic tests, and this is standard among doctors. This injury, not to that extent, SI joint problems can mimic lower back problems exactly. So, from my knowledge of spacecraft mutation, that was what came into my head. So, I thought, this is great. I'm going to get them to accept this. No. We've got all these doctors. Long story short, 6 months and the pain is so bad, I'm going to get my right leg amputated. I couldn't tolerate pain anymore. I was sleeping for 10 minutes at a time. The pain wasn't coming from here, it was coming from there, but that's where I felt it, and no one would do anything about this. Through a miracle that I won't get into here, I was 3 weeks away from that, I met this guy called Al Milas in Tampa. Someone told me, you need to call this guy. I said, who is he? He's a robotics engineer, designed the first artificial vision systems for robots. Call him up. Why? Because this was a doctor, Dr. John Young, Largo, Florida. He had horrible back pain. He nearly lost his job because of it. All the doctors said nothing could be done. He went to AIAA, developed a robot with a grant from NASA, Martin Marietta, the Department of Energy. NASA's forgotten all about it, so is Lockheed Martin. So anyways, we're going to use it for astronauts. I'll come to that in a minute. Over the phone, with no MRIs, no X-rays or anything, had me move in certain ways. He says, it's your SI joint. I nearly fell out of the bed. This is the first person I agree with me. The best spinal doctors in the world who do wonderful things, don't get me wrong, but they wouldn't listen to me because they didn't have a medical degree. One of them said, you only have an engineering degree. So what this robot does is it takes lumps of scar tissue and it all adhere together and it realigns the fibers panel. There's nothing like it in the world. So clinically, we've got about a dozen of these. In fact, they've got the latest generation. It cuts through scar tissue like that. One of the most amazing things I saw, and Al doesn't advertise this, was a burn victim. He was a young kid from what's the university in Tampa, USF?
Yeah.
USF. He'd been in a car crash and he was horrifically burned. He had all this masses of scar tissue. Coming to the clinic with a hoodie, over 3 weeks, Al reduced that thick scar tissue down a purple blotch. And it was pretty incredible. So he had to prove to NASA that this thing could do what no human could do and do it faster for things that a human could do. So they took 2 groups, a control group with a massage therapist and a robot, and they had people with similar scar tissue from operations. They used a biopsy before and after and under a scanning electron microscope. The robot was 400 times faster. So how do you measure that? What's the metric? Well, when the muscles release, the lactic acid comes out, goes into the urine, so they would measure the levels of lactic acid. But how to tell if the fibers were undone? Well, we use the scanning electron microscope. And you actually see these clumps of scar tissue starting to reorient. So Al worked on me. He saved my leg from being amputated. I then had, because every muscle in my body had contracted, and the joints had all swollen up. It was the worst pain. I can't even begin to describe how bad that pain was. Every muscle had contracted. And it was a feedback loop. The more pain that I had, the more in a fetal position I would go. The more in a fetal position, the more muscles would contract, etc. So I had 1,533 hours of physical therapy to get to the stage where I was able to walk properly, my arms moved, etc., etc. And I had 2 years laying on the floor of the house. So during this time, 2 news reporters heard about me, Fox News and ABC News. I don't know how they heard about me, but they sent me letters. We heard that you're a layman and you've found this very rare problem we've never seen before. Can we talk to you about it? So they ran programs all over the world, but it was interesting when they came in the house. Medical reporter from ABC News, she was a highly qualified doctor. She came in and she said, so you've diagnosed this problem and Dr. X, Y, Z was unable to do it. But then she said, how did you do it? Like you would speak to a child thinking that I've got someone else. I said, well, we can do it two ways. We can look at these models, or I hope you're up in Newtonian mechanics and Jacobian matrices because we can do a shear analysis. And I pulled out all of these documents, the formulas. So that program went worldwide. And then I left my email. I had people calling me, Dave, can you help me? And I was able to help some of these people there. This was a comment from one veteran. This was a British serviceman who was in absolutely horrific pain. It is. I get these phone calls all day long. These veterans have two images. They have what's called the Facebook image and the real image. No matter how much pain they're in on Facebook, and it's the same with civilians, they're always happy. They're at a restaurant. They're out fishing, etc. But the reality is that back pain, severe back pain, it can just destroy your life. It really, really can. I'm not talking about an ache. I'm talking about pain that makes you not move. So, my wife went through the roof at this. A few years ago, to prove the doctors wrong, I strapped on an SF-10E military parachute and did my first jump in over 30 years. She was on the drop zone, and when you come down a military chute, it comes down hard because if there's people shooting at you, you want to get down quick. With civilian parachutes, you can stand up, you can do whatever. These things come down quick. Now, you normally have both feet and knees together, hit the ground, you roll. My leg, the nerves were so badly damaged that when I thought my feet were together, the right foot was an inch lower than the left. I landed in one leg. I thought my spine had broken. And my wife came running over and also had another year of therapy. But this gave hope to veterans. I've had veterans contact me and say, Dave, I was thinking of doing something really, really bad. And this has given me some hope. And that's the good thing that's come out of this. So in summary, if I didn't have that engineering knowledge and I didn't stick to it as I've been taught as an engineer, if you know your calculations are correct, if your theory is correct, you must stick to it no matter what. And as a result, I'm not 100%. I mean, it takes me about an hour a day to get up and, I've got a lot of